Okay, hello. We are in section 3.2. We're going to tackle a couple of objectives, and that is to describe the tangent and unit tangent vectors for a vector valued function. So let's get to it. All right, when we take a look at the derivative of a vector valued function, you would think it has something to do with tangent lines and stuff like that. So it would kind of be natural that the vector that we get when we take the derivative of a vector valued function will actually be a vector that's significant to the actual curve that is generated by the vector valued function. So that's exactly what's going to happen, is that the derivative will end up being a vector that will actually be tangent to the curve. So here, and we're defining this tangent vector, C is a curve of a vector valued function r, and we assume that r prime exists, and when t is equal to t naught, so we're just picking some value t naught, a tangent vector v at this point t naught is going to be a vector such that when the tail of the vector is placed at the point r prime of t on the graph, then the vector that they're talking about here is actually tangent to the curve. So vector r prime of t is an example of a tangent vector at a particular point. Okay, all right, let's take a look at an example and maybe take a look at this from a graphical point of view. So our vector valued function is going to be t in the first component and sine 2t in the second component and cosine 3t in the third component. So let's find the derivative first, and so that's going to be our first step. R prime of t is going to be, well, the derivative of t is just going to be 1. The derivative of sine t is going to be cosine, but there's a 2t inside, and so we'll multiply by 2 from, because of the chain rule. And then derivative of cosine is going to be sine, negative sine 3t, and then since there's a 3t in here, we'll multiply by the derivative of 3t, which is 3. So now we have the derivative. So if we take a look at this at a specific point, then we should get the derivative there. So let's see, r prime of pi over 3 is equal to, well, let's put pi over 3 in here. There's no t for the first component. The second component is going to be 2 cosine 2 times pi over 3, so that's just 2 pi over 3. And then the third component is negative 3, and then we have sine of 3 times 3 pi over 3. So that's just pi. So I suppose that would cancel and we just get sine of pi, and I believe that's equal to 0. Cosine of 2/3 pi, let's see, cosine of 1/3 or pi over 3 is 1/2, but it's in the second quadrant, so that's going to be a negative 1/2 because cosine's negative in the second quadrant, and multiply it by 2, so that's just 1, negative 1, and then this is 0. Okay, so that's your derivative, or that's your derivative at that point. By the way, let's figure out what r of t is. R of t, not r of t, but r of pi over 3. So this is going to be pi over 3 because that's the t value, and then we just have a regular sine pi over 3, and then oops, that's multiplied by 2, and then we have a cosine of 3 times pi over 3. Okay, and I believe these are going to be, well, this is just pi over 3, you can't do anything about that. Sine 2 pi over 3, sine of pi over 3 is root 3 over 2, and it's in the second quadrant, but it'll stay positive, so that's root 3 over 2. and then the cosine of pi is, I believe, -1. Yes, -1. All right. Okay, so let's take this information and bring it to our graph, just so we can get a visual of what's happening. All right, this is our curve. It's actually a nice curve. So t, it's an interesting looking curve. It looks like it's spiraling. Going along the x-axis, the positive x-axis, it looks like it's just going forward. And then it almost looks like a sine or cosine curve. But if an interesting point of view is that if you look at it directly from the positive x-axis, if I can get this figured out, you can see that it looks like some sort of a polar coordinate graph. Okay, I can't seem to get it, so let's just leave it at that. Anyways, the point that we're looking at is pi over 3 and then √3 over 2 and then -1. So let's take a look at that point. That point is indeed on the graph, so that's good news. Now let's take a look at that vector that we found as a vector, and I believe that vector was 1, -1, 0. So let's throw in the 1, -1, 0. That's 1, -1, and 0. So as a vector, it doesn't seem to be that significant coming from the origin, because that's how vectors usually are drawn, right? You look at it from the origin in standard position. But if we take that point that we got from before, I'm just going to copy that, and I'm going to go back to the vector and change the initial point from 0, 0, 0 to this other point that's actually on the graph. Then we can see that this actually is going to be a vector that's tangent. So you have to look at it from many different points of view to actually see that it is in fact tangent to that curve. Okay, so that's our tangent vector. Now, because we have a point and a direction, we can actually define a tangent line, or we can find a tangent line. So let's do that just for fun. Let's actually find the tangent line for this function at this point. So we have a point here and a direction here. So the direction comes from the derivative, the point comes from the original function, and then your line, let's call it L of t, is just going to be your point. That's pi over 3 √3 over 2 comma -1 plus t times 1 -1 0. All right. Okay, so if we write this in parametric form, we got pi over 3 plus t, that's your x, and then your y is √3 over 2 minus t, minus 1 times t, and then your last component is just going to be -1. Okay, so let's draw this line to see if it actually works out to be the tangent line, and I hope that it will be. We'll draw a space curve, and our first curve is our first component is pi over 3 plus t. Our second component is a square root of 3 comma or divided by 2, and then we'll subtract the t, and then the other one is just constant. All right, let's take a look at the graph. Let's do this in like just primary colors. So here we go. It is the tangent line at that point. All right. Okay, let's define a new tangent. Well, it's really just normalizing this vector. So there will be some times where we might just be interested in the direction of the line instead of messing around with how long the tangent vector is. We'll see in the next section or two that the length of the tangent vector, the derivative, is actually going to have some meaning to tell you something about the curve. But for now, let's say we don't care about that meaning. We don't care about the length of the tangent vector. We just want the direction. And generally, when you just want the direction, you make something into a unit vector. So if you remember, to make things into a unit vector, you just divide by its magnitude. So our unit tangent vector is going to be officially defined as capital T. I know little t is a parameter, but capital T will be our unit tangent vector. And that would be just a derivative divided by the magnitude of the derivative, just to make sure it has length 1. And of course that would work only if the magnitude of the derivative is not equal to 0. Alright, so let's take a look at what we did already. And we found the derivative to be this expression over here, r prime of t is equal to this whole thing. So let's not redo that work. Let's just say that's r prime of t. And so we are interested in the derivative of that. So let's find the derivative. I'm sorry, we're interested in the magnitude of that. So let's find the magnitude of r prime of t. And that is going to be the square root of 1 squared plus 2 cosine 2t quantity squared plus 3 sine 3t quantity squared. Now technically it's a negative sign, but it's going to get squared anyway, so it'll become positive. And I'm afraid there's no simplifying this much further, so we're just going to have to leave it like that. And I suppose if we want to write it out as a unit tangent vector, I can repeat this, rewrite this by distributing this 1 over this magnitude scalar into all those, but I think I'm just going to leave it on the outside as per the definition, or just slightly rewritten. So our unit tangent vector, that's t with an arrow, capital T with an arrow, I'm sorry, that's a capital T of t, and that's capital T with a vector notation, is going to be just 1 over the square root of 1 plus, I'll just call it 4 cosine squared 2t plus 9 sine squared 3t. And then we'll divide it by, or we'll multiply it by the vector 1, 2 cosine 2t, and then 3, negative 3. The negative here is important because we're not squaring it, sine 3t. Okay, that is your complicated looking unit vector, unit tangent vector. Let's do a couple more. Let's do this one, and we'll see that some nice function, and I'll say nice in quotes, lead us to some pretty interesting unit vectors. Alright, so let's find r prime of t first, because that's what we've been doing, and this is going to be 2 negative 2 sine 2t, and then the second one is going to be a positive 2 cosine 2t, and then we find its magnitude, r prime of t, and this is the square root of 2 sine 2t squared plus 2 cosine 2t squared, and we get a 4 out of both of these, and then what we have left is a sine squared 2t plus cosine squared 2t. So we have the same arguments for the sine and cosine, and they're being squared, and so we know that this whole thing's going to equal a 1, and we get the square root of 4, which is equal to 2. So conveniently, our derivative, or the magnitude of our derivative, is just a constant, which may or may not happen a lot, but then we find our capital T of t, our unit tangent vector, and that's going to be 1/2, and then we have negative 2 sine 2t and positive 2 cosine 2t. So we can see that the 2's just cancel, and we simply get a negative sine 2t and a positive cosine 2t. Now, if you want to take the time and find the magnitude of that, you'll see that the magnitude is actually equal to 1, and this in fact is a unit vector. Okay. All right. I think we have one more to do here, so let's just do this example real quick. I don't think there's going to be any simple, nice results like we've had here. This will be very similar to the one we have before, but let's go through this anyways just to practice. Our derivative is going to be given by 6t minus 2, and then we have 0, and then we have 12t squared, and then we have just the constant 6. So let's find the magnitude of that, and that is going to be the square root of 6t minus 2 quantity squared plus 12t squared quantity squared plus 6 squared. So yeah, I don't believe that there's ways to simplify this. So let's just leave it at that, and then the unit tangent vector is going to be 1 over this whole thing, 6t minus 2 quantity squared plus 12t squared quantity squared plus 6 squared, and then 6t minus 2, 12t squared, and 6. Alright, this goes to show you that in 2 of the examples that we've had, we have a complicated looking unit tangent vector. And for this one, where we have a sine and a cosine in 2 of the components, in this case it's only 2 dimensions, so in both of the components we get a nicer unit tangent to deal with, because the r prime, the magnitude of r prime happens to be constant, and so that's actually a very interesting phenomenon when we run into something like that. In any case, here is the unit tangent vector, and this is the significance of the unit tangent vector, is that you get a tangent vector of unit length, and you know that really gives you the only piece of information that's needed for creating a tangent line, and that's the direction. Okay, I hope that helps. Good luck.